numerical calculation of orbital and epicyclic frequencies around compact objects. On these studies, I'll collaborate with Dorota Rosińska, Wojciech Kluźniak, and Nick Stergilas. Why the epicyclic frequencies are so important? Because there are many models involving epicyclic frequencies to explain origin of quasi-periodic oscillations visible in low mass X-ray binaries. The first kilohertz quasi-periodic oscillation have been observed by the X-ray satellite RXT. The quasi-periodic oscillations are the most important scientific result of Rossi X-ray Time Explorer. In this picture, you can see the power spectrum of the system scope X1, and you see the two-peak QPO. To date, kilohertz QPOs have been discovered in about 20 neutron stars, low mass X-ray binaries, and mostly showing double peaks in the range of 200 Hz to 1.3 kHz. And also there are systems showing 3 or more peaks of QPOs. As I said, there are many different models to explain the origin of quasi-periodic oscillations. Most of them involve orbital and two epicyclic frequencies, radial and vertical. These epicyclic frequencies correspond with vibration of the particle in orbit in the radial and vertical. For example, Stella et al. Model involve orbital frequency as a upper kilohertz QPO, and the difference between orbital and radial epicyclic frequency as a lower kilohertz QPO. Other model developed by Abramowicz and Kluźniak involve two epicyclic frequencies, radial as a upper QPO and vertical as a lower. The effect of the spin of the epicyclic frequencies around black hole. We know that in Newtonian gravity, orbital frequency, radial and vertical, are equal to each other for non-rotating case. In a Schwarzschild metric, we have orbital frequency is bigger than radial epicyclic frequency. In the case of Kerr metric, we have a frame grading, and then vertical epicyclic frequency is lower than orbital in the case of prograde orbit. In this picture, we can see on the horizontal axis we have a radius of the disk, and for horizontal axis we have a frequency of epicyclic frequencies and orbital. This picture corresponds with in the case of non-rotating case, and we see that orbital frequency and vertical epicyclic frequency are equal to each other, and the radial epicyclic frequency is lower than the orbital. For moderate rotating black hole, vertical frequency is lower than the orbital, but the difference is very small. For rapidly rotating black hole, difference between vertical frequency and the orbital is much higher. And what we see also, we know that from Rayleigh criterion, then the radial epicyclic frequency goes to 0 at the ISCO, marginally stable orbit. It's here. We see that for a rotating black hole, ISCO is drawn to in the direction of the black hole. To perform our calculation, we use two models of strange quark star and neutron star. To describe strange quark star, we use MIT-Beck model, in which quark matter is composed of massless U and down quarks, and massive S quarks and electrons. This equation of state could be described by simple analytic formulae, where P is the pressure and rho is the mass energy density, rho 0 is the density at the surface of the star. Equation corresponds to self-bound matter with density rho 0 at 0 pressure and with a fixed sound velocity at all pressures. For fixed value of A, all stellar parameters are subject to scaling relations with appropriate powers of rho 0. For example, for these quantities. And to describe neutron star, we use FPS equation of state, which is a tabulated equation of state developed by Friedman et al. Here we see mass-radius relation for two equations of state. Black solid line corresponds to non-rotating case, red solid line with Keplerian angular velocity, and the dashed line corresponds with different spin frequency of the star. We see that that strange stars are more compact than neutron stars because change of the mass and the radius, even for spin frequency equal to 900 Hz, is very small than in the case of neutron stars. To perform our calculation, we used RNS code developed by Nick Sterbulas. We have calculated axisymmetric models of strange quark stars and neutron stars and their exterior metric using a highly accurate relativistic code. The equilibrium models are obtained following the Kerr method, in which the field equations are converted to integral equation using appropriate Green's function. We have computed the metric outside uniformly rotating quark stars and neutron stars of masses and rotation rates that may be typical of compact stars which have been spun up to accretion in low mass X-ray binaries. Okay, let me say about results. Here we see on the horizontal axis we have a radius of the disk over the gravitational mass of the star. On vertical axis we have frequencies. These are results for 1.4 solar mass strange quark star. Red black line corresponds with rotational frequency equal to 600 Hz, and the red corresponds with about 1.2 kilohertz. Okay, we see that for a moderate rotating strange quark star, we have similar behavior as in the case of black holes. Vertical epicyclic frequency is belong to orbital. For rapidly rotating strange quark stars, we have opposite effect. It is a completely new effect for in this case. We see also the ISCO, which corresponds to the radial epicyclic frequency equal to 0. We see that ISCO is pushed away of the stars in the case of rapidly rotating strange quark stars. This is the same plot, but for a mass 1.9 solar masses of strange quark stars. The effect, we see that we have the same effect for rapidly rotating strange quark star. The vertical epicyclic frequency is higher than orbital. These are results from very low mass strange quark stars, and the difference between orbital and vertical epicyclic frequency is much higher. Here we see the plot of on the vertical axis. We have a difference between vertical epicyclic frequency and orbital. The sign of this difference corresponds with the direction of the precession of the disk, because this difference of these frequencies corresponds to length-stealing precession of the disk. So if we have a positive sign, we have a prograde orbits, and negative retrograde orbits. To check behavior of this effect when the vertical frequency is higher than orbital, we perform calculation in Newtonian gravity. Amsterdamski et al. Shown that ISCO exists in the Newtonian theory for high elliptices higher than 0.8. And in this year, my collaborators derived analytic formulae for epicyclic frequency in Newtonian theory, and we performed numerical calculations of very low strange quark stars with mass about 0.0001 stellar mass, solar mass, and the numerical in the right picture we see that solid line corresponds with analytic formulae, and the points corresponds to our numerical results. We see that agreement is excellent. We check, we perform our calculation to all elliptices, and the agreement is with Newtonian, with this formula derived by Kluźniak et al. Are excellent. In the case of neutron star, we have the same effect, but only for rapidly rotating neutron star. In this picture, you can see results for 1.2 solar mass neutron star. And this, we see that on this plot we have a plot on the horizontal axis. We have a mass of the star, of the neutron star, described by FPS equation of state. On the vertical axis, we have a frequency. We see that for the neutron star in this case rotate at mass sharing limit. We see that for neutron star below the 1.5 solar mass, the effect and the vertical epicyclic frequency is higher than the orbital. And summarize, stellar spin has two opposing effects on epicyclic frequencies: frame dragging and stellar oblateness. Frame dragging decrease the vertical epicyclic frequency and increase the radial epicyclic frequency of prograde orbits. Stellar oblateness increase the vertical frequency and decrease the radial epicyclic frequency. In rapidly rotating strange quark stars, the effect of oblateness dominate the behavior of the vertical epicyclic frequency near the star. The effect is also visible in rapidly rotating neutron stars, but is much lower than in the case of strange quark stars, because we use very soft equation of state of neutron stars. We check. We have to perform a calculation with equation of state of neutron star with more stiffness. The nodal precession rate in rapidly rotating strange stars orbits is unusually high.
Thank you.
Thank you.